Section 11.8 deals with polysaccharides. Just as two sugar units are linked together to form a disaccharide, additional units can be added to form larger saccharides. Nature does just this in forming polysaccharides, which are condensation polymers containing thousands of units. Because of their size, polysaccharides are not soluble in water, but some polysaccharides become viscous when heated in water because of their many hydroxyl groups. Thus, the polysaccharide known as starch can be used as a thickener in sauces, gravies, pie fillings, and other food prep. As shown in Table 11.4 here on the screen, the properties of polysaccharides differ markedly from those of monosaccharides and disaccharides. So we see here that the molar mass or molecular weight of monosaccharides and disaccharides is relatively low, whereas polysaccharides can be huge, thousands of grams per mole or atomic mass units. The taste of monosaccharides and disaccharides like glucose and fructose and sucrose is sweet, whereas polysaccharides like starch, if you've ever tasted raw starch, I don't know why you want to do that, but anyhow, it's tasteless. Solubility in water. So if you think about table sugar, well, that's really soluble in water, right? That's a disaccharide, whereas polysaccharides are going to be pretty much insoluble in water, very slight um, solubility at all, even at high temperature. And then the size of the particles, well, monosaccharides and disaccharides can pass through a membrane like a semi-permeable membrane that you might find in a dialysis bag, whereas polysaccharides are they're just too big. They're not able to pass through those small pores. Starch is a polymer consisting entirely of D-glucose units. It's the major storage form of D-glucose in plants. Two starch fractions, amylose, which is 10 to 20% of starch, and amylopectin, which is 80 to 90% of starch, can usually be isolated from plants. Amylose is made up of long, unbranched chains of glucose units connected by an alpha 1,4 linkage. And this same type of linkage is the one that we saw in maltose. The long chain, often containing between 1,000 and 2,000 glucose units, is flexible enough to allow molecules to twist into the shape of a helix. An important test for the presence of starch is the reaction that occurs between iodine, I2, and the coiled form of amylose. The product of the reaction is deep blue in color, and you can see that shown here in this figure. And it is thought to consist of the amylose helix filled with iodine molecules. The same iodine reaction is also widely used to monitor the hydrolysis of starch. The color gradually fades and finally disappears as the starch gets hydrolyzed by either acid or enzymes to form dextrins, which are smaller polysaccharides, then maltose, and then finally glucose. The disappearance of the deep blue iodine color is thought to be the result of the breakdown of the starch helix. Amylopectin, the second component of starch, is not a straight chain molecule like amylose, but contains random branches. The branching point is the alpha 1,6 glycosidic linkage, and you can see that shown here in figure 11.33. There's usually 24 to 30 D-glucose units all connected by those alpha 1,4 linkages between each branch point of amylopectin. These branch points give amylopectin the appearance of a bushy molecule. Amylopectin contains as many as 100,000 glucose units in one gigantic molecule. The polysaccharide glycogen is sometimes called animal starch because it is a storage carbohydrate for animals that is analogous to the starch of plants. It's especially abundant in the liver and muscles where excess glucose is taken in by an animal and is stored for future use. On hydrolysis, glycogen forms D-glucose, which helps maintain normal blood sugar levels and provides the muscles with energy. Structurally, glycogen is very similar to amylopectin, both containing both the alpha 1,4 and the alpha 1,6 linkages between the glucose units. The main difference between amylopectin and glycogen is that glycogen is even more highly branched. There are only 8 to 12 D-glucose units between the branch points, unlike with the amylopectin, where there was a lot more space between them. Cellulose is the most important structural polysaccharide. It's the material in plant cell walls that provides strength and rigidity. Wood is about 50% cellulose. Like amylose, cellulose is a linear polymer consisting of D-glucose units joined by 1,4 linkages. It may contain 300 to 3,000 glucose units in one molecule. The main structural difference between amylose and cellulose is that all the 1,4 glycosidic linkages in cellulose are beta instead of alpha. This small difference causes the shapes of the molecules to be very different. The alpha 1,4 linked amylose tends to form loose spiral structures, whereas the beta 1,4 linked cellulose tends to form extended straight chains. And these chains become aligned side by side to form well-organized water-insoluble fibers in which the hydroxy groups form numerous hydrogen bonds with the neighboring chains. These parallel chains of cellulose confer rigidity and strength to the molecules. Although starch with its alpha linkages is readily digestible, humans and other animals lack the enzymes necessary to hydrolyze the beta linkages of cellulose. Thus, cellulose passes unchanged through the digestive tract and does not contribute to the caloric value of food. However, it still serves as a useful purpose in digestion. Cellulose, a common constituent of dietary fiber, is the roughage that provides bulk, stimulates contraction of the intestines, and aids the passage of food through the digestive system. Animals that use cellulose as a food do Animals that use cellulose as a food do so only with the help of bacteria that possess the enzymes that are necessary for breaking it down. Herbivores such as cows, sheep, and horses are good examples. Each has a colony of these kind of bacteria somewhere in their digestive system. The simple carbohydrates resulting from the bacterial hydrolysis of cellulose can then be used. Fortunately, the soil also contains organisms with appropriate enzymes. Otherwise, debris from dead plants would accumulate rather than decompose. And so by now, you should be able to describe the four major functions of carbohydrates, classify carbohydrates as mono, di, or polysaccharides, identify a carbon in a molecule, draw pairs of enantiomers using wedges and dashes, use Fisher projections to represent D and L enantiomers for sugars, identify the following functional groups. So hemiacetal, acetal, hemiketal, and ketal. Draw Haworth projections of carbohydrate anomers. Classify monosaccharides as aldoses and ketoses. Classify monosaccharides according to the number of carbons they contain, so triose, tetrose, pentose, etc. Describe the four important monosaccharides. Describe the purpose of Benedict's test, where we um, oxidizes sugar, and then in turn, copper 2 gets reduced to copper 1, so it goes from blue to red. We should be able to identify glycosidic linkages. Describe three important disaccharides. Describe the linkage in disaccharides, write reactions of condensation and hydrolysis of a disaccharide. Describe the uses of three important polysaccharides, and describe the linkage